Buenas tardes, bienvenidos y bienvenidas a esta sesión 365, si no me equivoco ya, del Ateneo de la INA. He perdido la cuenta, 26, 27 años haciendo el Ateneo, así que es un placer volver a estar con todos vosotros en una sesión que nos hace una ilusión especial porque bueno, tenemos una visita. Siempre viene gente de muchos lugares de España, pero en alguna ocasión incluso también de fuera de España, como es esta ocasión. Enseguida voy a pasar a presentarlo y pasaré a hacerlo en inglés por respeto hacia nuestra ponente. Pero antes quería, como siempre, agradecer que estos 26, 27 años que llevamos de Ateneo ocurren gracias a muchas personas y a unas cuantas instituciones, no solo el Ateneo de la INA, también lo es del ITRESAI, de la Cátedra Sanca de Desarrollo Tecnológico, que serán quienes en la figura de Juan Pablo luego cierren esta sesión del Ateneo. So now I switch to English. So it's our great pleasure, our great honor to have you here today. Professor Kar-Narayan comes from the University of Cambridge. So it's been an express trip also. So you came today and you go back tomorrow. Thank you very much for doing that, all the way from Cambridge to here. And it's our great pleasure to have you here. And Julia Herrero will be the person who will be presenting her, second Ateneo in a row, because you were also presenting the last one.
I'm not doing that next time.
This is the last time. So thank you also, Julia. She's a colleague of us here at the School of Engineering and Architecture. Thank you both for being here, and Julia.
Thank you. Well, I'm really happy to be here presenting Sohini Kar-Narayan. She's a full professor at the University of Cambridge at the Department of Material Science, where she leads quite a big group of people from different disciplines, from chemistry, biology, physicists, engineers, about 15 people also, and growing. She works on materials, actually on functional nanomaterials for devices with different applications, from energy to sensing and medical applications. And I think she's going to be talking on all of it today. And she's also a fellow of Clare Hall of the University of Cambridge. She has a PhD in physics from the Indian Institute of Science in Bangalore since 2009. And she has been at the University of Cambridge since then, and that's where we met. And we've been remembering that we're very friends since 16 years. So we met there in Cambridge. Well, in 2012, she got a very prestigious fellowship from the Royal Society, the Dorothy Hopkins Fellowship. And she has been awarded with 2 European Research Council grants, one starting grant in 2015, and one consolidator grant just last year. So she's starting to spend all that money. She has so many, the list of things that she has achieved is enormous. So I'm just going to say a few of them, but she's now, she has founded a spin-off from the University of Cambridge. She's the co-founder of the spin-off and the director. The company is called Sense Ltd. And they're trying, well, she will talk about it, but they're trying to offer sensing devices for precision surgery. And then, well, just to summarize, just to give you a flavor of what kind of prizes she's getting, well, she got the World Economic Forum Young Scientist Award, and she also got last year the Royal Society Chemistry Teacher Day Prize, and in 2021 she was awarded with the top 50 woman in engineering by the Women in Engineering Society, and just yesterday she got yet another new prize, and she was awarded with the Innovator of the Year prize by the Women Leaders in Electronics. Apart from that, she's an excellent co-worker. She's always helping everyone around. She's one of these persons that thrives with touching things in the lab, and she's really good with her hands. She's excellent at playing badminton and cooking, and well, everything she does great. And I'm really happy that the Ateneo gave me the opportunity to spend one more day with you. And well, I hope you like the talk, and thanks for coming.
Okay, good afternoon, everyone. First of all, thank you, Julia, for the very lovely, very kind introduction. Really appreciate it, and thank you, to the Institute here for hosting me. I just found out that this lecture series has a sort of a long and illustrious history, so I'm really very honored to be part of it. So many thanks for having me. I'm going to talk a little bit about our work. I'm going to try and touch on as many aspects as I possibly can in the next. Within the next hour. So very broadly speaking, we work on functional materials and devices for energy sensing and biomedical applications. But before I dive into that, I just want to tell you a little bit about myself and how I got here. So just a very quick, Julia's done a great job of summarizing it. But just to tell you that when I started my PhD, I trained as a physicist, and I was working on very much my subject area was experimental condensed matter physics. I was working on magnetic oxides, manganite. These are manganites that could be used for applications in memory devices. So there's me during my PhD. I used to work on these ultra high vacuum, low temperature scanning tumbling microscopes that I built myself, and that's kind of where my love for experimental science really grew. And then, so these were oxides, as I mentioned, magnetic oxides. From there, I moved to ferroelectric oxides, so different class of oxide systems, where I was looking at electrocaloric effects during my postdoc years in Cambridge. And electrocaloric effects, these are electric field-driven temperature changes in solid materials that you can use for instance, solid-state cooling applications. This is, of course, when I met Julia. This is a picture of us from very long ago. She is actually one of my oldest, dearest friends, and one of the nicest, kindest people I've known, and I've really cherished this relationship from 16 years ago. And we were just saying it's almost to the day that we met. And then the start of my sort of independent research began with the fellowship, the Royal Society for International Fellowship, where I decided to move away from oxides to try something new. And this is where I chanced upon, from ferroelectric oxides, I chanced upon ferroelectric polymers. And mind you, till this point, I had never touched an organic material. I had no idea what, how to work with these or what these were. But I thought, I would like to apply some of the skills, the expertise to a different class of materials. And that's how I chanced upon ferroelectric polymers, and this is also where I was sort of starting to grow my own group. And then a series of, over the last few years, we've diversified, again, thanks to very generous funding from the ERC, to various, different areas. And I will touch upon some of these today, to the point where, of course, alongside my professorship, I've also co-founded this company called ArcuSense, and we're developing essentially a product, a med tech device, a medical technology device. And so it's quite a journey, as you can imagine, from someone trained as a physicist working with oxides, all the way to someone working. So this actually, Vikas here is the surgeon that I work with. So I work extensively these days with clinicians and surgeons. So it's been quite a journey. And mind you, at some point I transitioned from a physics department to a material science department, and now I identify as such, I guess. And this is just to say, and of course, this is currently my group, and I do work with people who come from a physics background, who are chemists by training. I work with a lot of engineers in my group, and also a couple of biologists. And this is just to give you a flavor of the interdisciplinary nature of the research that I do. So that's just a little bit about me and how I got here. I'll now dive into some. Oh, sorry, that was just a picture from literally last night, where I was awarded an award for contributing to the electronics industry, which is, again, I'm quite proud of that. Anyway, so I wanted to start with giving you a flavor of the scientific focus. what is it at the sort of heart of the research that I do. And I always like to start this with a question that I use for my first year material science undergraduate students. So I did this course where I have 300 students in a lecture hall. None of them know what material science is because it's not a subject taught in schools. And I asked them, right, so how strong is a bar of copper? And I bring in these very small, thin bars of copper, and they all look identical. I look around the room, I find the most athletic looking person I can, student, and I was like, here, why don't you give this a try? Like, just see how strong this piece of copper is. And they try to bend it, and they try really hard, and there's nothing they can do to get it to move. And then I'm like, are you sure you're doing this right? And then I'm like, here, let me show you. And I take another piece of copper, and I bend it, and it's super easy. And they're really confused, like, how is it possible? So the fact is that they look alike, they look identical, they feel the same, they weigh the same. But of course, what is different and what the student doesn't know yet is the fact that if you look closely with the microscope at even the surface features, you'll notice that the microstructure is very different. These copper bars, of course, are made of tiny crystallites of copper atoms, which arrange themselves in this grain-like formation, and there are grain boundaries between these grains. And the difference between the piece I give the student and the piece that I give myself is the processing. So one of the pieces I've actually annealed at a very high temperature for a considerable amount of time. It's the same copper, but just by changing the processing, I can actually change the grain structure. I can make the grains much bigger, fewer grain boundaries, so there are fewer there are fewer defects over which, or fewer grain boundaries over which dislocations can get impeded, right? And that makes this material much softer. This has other implications as well. If you look at the conductivity, it is quite different between these two pieces of copper. Again, they look the same, but microstructurally they're different, and hence the properties are different. So this is how I hook my first year material science students. At this point, everyone wakes up and they really want to understand what this is all about. But this is basically the scientific focus of my research. I'm really interested in understanding how different processing conditions can be used to manipulate structure at the micro or indeed the nanoscale, and how this can be used then to to control or to enhance specific properties, and not just for metals, and not just talking about mechanical strength, but looking indeed at functionalities, looking at actual functional materials and trying to use the same idea to enhance the properties of various functional materials. And by functional materials, I mean any material that is responsive, where you can apply some sort of stimulus and the material has a response, which can be useful either for sensing or for indeed other applications. So broadly speaking, the materials I work with, the application areas are in energy, sensing, and of late a lot of biomedical devices. So at the heart of all of this, of course, as I mentioned, are materials with different functionalities. And because properties of materials are different at the nanoscale than they are from the bulk, it is important to be able to characterize these materials at the nanoscale. So we do a lot of atomic force microscope-based measurements to understand functionality at this landscape. And then how do we go from nanomaterials to devices? So the way we do it is we use additive manufacturing or printing techniques, some advanced printing techniques, where we can make inks of these functional materials, and then we can directly print them layer by layer into devices. So quite a bit of device engineering work goes on in the group as well. So just to give you a flavor, in terms of energy, we make various kinds of devices. So some examples here, we have devices that can harvest mechanical energy from the environment, just ambient vibrations, and convert that into some useful electricity. We have similar devices that can harvest waste heat in the environment and convert that into electricity. And we're also interested in making these flexible and stretchable so that they can integrate better within our environments. In terms of sensors, there's quite a few things, and I will try to touch on as many of these as possible. But of late, we've been developing microfluidic devices or microfluidic sensors. Also looking at sensors that can be used to sense what single cells are doing. Sensors which can look at various biomarkers in sweat rather than having to draw blood to look at various biomarkers. And also, using and trying to see whether these can be integrated into wearables, like whether we can actually have proper wearable sensors by integrating this into clothing through smart textiles. And in terms of biomedical devices, again, we work quite a bit on developing sensors, for instance, to aid orthopedic surgery, or indeed to build new soft robotic systems that can be used to again help in error-free or minimal error surgeries. And again, at the sort of heart of all of this, we use additive manufacturing to actually build our devices, and we use scanning flow microscopy to study our devices. So the way I've structured this, again, is to try and touch on as many things as I possibly can, is I'll give you 2 examples of each of these subroutines, right? And just to give you a flavor. I will warn you, I might go a bit fast, so please do forgive me, but I just want to cover as much ground as possible so that, we might have some time to have discussions, now or later. So let's start with energy, functional materials and devices for energy. So the 2 examples I'll pick up on are devices where we can convert ambient mechanical energy or ambient thermal energy into electricity. And the way we go from mechanical to electrical is using what are known as piezoelectric and triboelectric materials, and going from thermal to electrical using thermoelectric materials. And the reason we're doing this, I don't think I need to motivate this. Obviously there's we all know about the global energy crisis, etc. And of course we're looking for ways in which we can power entire cities, but I'm actually looking at something on the other side of the spectrum, and that is how do you actually power tiny sensors that may be, that could be embedded within our environments. These could be sensors embedded within buildings or infrastructure to, for instance, monitor, whether cracks are developing. These could be sensors within our bodies to monitor physiological parameters, and so typically, the idea is to have a network of these sensors via the Internet of Things, where these sensors can all talk to each other, talk to some central unit, and via the use of the sensors, we can possibly make our use of energy and resources a lot more efficient. But how do these sensors actually? How do you actually power the sensors? These are tiny, tiny sensors, so they need very small amounts of power. I'm talking about microwatts or even less. And you might think, well, that should be easy to do. Typically, the way this power is produced is using batteries, right? But batteries, as we all know, are they need recharging or replacing once they're out of juice. And if you think of making these sensors really tiny, maybe embedded in walls or within the bodies, how do you go about changing so many batteries? So the question is, how do we actually power the Internet of Things? So one way to do this is to harvest energy from the environment itself, that where these sensors are operating, and use that and try to convert that into electricity that can run the sensors. So I asked this question again to my students, what are the forms of ambient energy you can think of that we can harvest? And immediately everyone goes, the sun. And absolutely, that's the abundant source of clean energy, etc. But if you live in England, you will know that the sun is not always accessible or convenient. And in fact, pretty much the entire time I've been with Julia today, I've been like, oh, it's so sunny out here. It's so amazing, because this is not something we normally get to experience in England, let's say. But also, there are geographical constraints, time of the year, etc. Also, indoors, for instance, you're not really going to get very much sunlight. So I've always been interested in heat and vibrations, particularly vibrations, because you're always close to something that is moving, and whether we can use this to, whether we can actually harvest energy from vibrations. So the reason this is, we've always had vibrations, right? And why now? So one of the main reasons is because the devices, so these wireless sensors that I'm talking about, their power requirements are actually reduced to such an extent that the energy that is available in ambient vibrations is, it is actually possible to match this up. And this has only happened, recently because of advances in engineering of these types of sensors. So one way that we can go between mechanical to electrical energy directly is using piezoelectric materials, right? And piezoelectric materials are essentially, these are materials which, due to their crystal structure, they're able to convert an applied stress or strain into, a voltage or a potential difference across the material. So we squeeze this material. There's you change the polarization, so there's you can measure a voltage across it, and it works the other way as well. You can apply a voltage to this material, and it will deform. So these are the same kinds of crystals that you find in like lighters, or even in ultrasound transducers. Yeah? So we've known about these materials, and typically they're ceramic in nature. So for instance, materials like barium titanate or lead zirconium titanate. However, there is a class of polymers that exhibit piezoelectric properties as well. But I should tell you that they're typically much poorer counterparts than the ceramics, which is why they've often been overlooked. And the reason for this is, like I said, piezoelectricity, it is rooted in the crystal structure, right? And polymers are not known to crystallize quite as easily as you would have in an inorganic material. So one way you can control crystallinity is reduce the size of the polymer, right? You just have, literally you have fewer molecules to work with, so you have a little bit more control over how these materials, how these molecules can be arranged. So size matters when it comes to piezoelectric polymers, but so does phase. So let me explain what that means. So here's a typical example of a piezoelectric polymer. It's called polyvinyl chloride. It has a very simple structure. So there's a carbon backbone, and it's got hydrogen and fluorine atoms scattered around it. Okay? Now this polymer can, the thermodynamically stable phase is what is known as the alpha phase, where the hydrogen and fluorine atoms are sort of randomly aligned across this chain. So for a material to be piezoelectric, there has to be a dipole moment somewhere in this chain. There has to be a polarization present. And the polarization arises from the difference in electronegativity between the fluorine and the hydrogen. So there's like a dipole moment across the chain. But in this alpha phase, you can see that, the dipole moment sort of, it's randomly oriented. So the net effect is that you don't have a piezoelectric material, even though there is a dipole somewhere in there. So ideally what you want is this beta phase, where you have all the hydrogens lined up nicely on one side, all the fluorines lined up nicely on the other side. So this is the all-trans configuration, such that now you have a sustained dipole moment or sustained polarization across the chain. So this is why phase matters. So it's not just enough to have PVDF, but you need to have PVDF in this particular beta phase. But like I said, this isn't the thermodynamically stable phase, so we have to work hard to be able to get to this. So we came up with a very simple way of, a simple processing technique. Remember what I was saying about how processing affects structure, affects properties. So we came up with this easy processing technique that helps us to control quite precisely both phase and microstructure in these polymers. And the method is as follows. So you start with a nanoporous template, and then we started using the anodized aluminum oxide. So these are actually filtration membranes. They're used in the medical industry as filtration membranes. The pores in this very thin membrane are nanosized. Yeah. And so what we do is we dissolve the polymer of interest, or you can even melt it and basically force it by capillary infiltration into these templates. And then you can carry out like a controlled evaporation or a controlled annealing to solidify these nanowires, and you can get rid of any extra material so that you have a template filled with these nanowires. Yeah? So it's a very versatile technique. You can just change the size of the template to play around with the geometry of the material. And here's, this was actually a surprise. This was actually my first PhD student, Richard, who was working on these materials at the time. And here are some SEM images kind of showing, you can actually dissolve the template away to release this kind of forest of nanowires. And what he found was, if you do some X-ray diffraction, the starting powder, or the starting material that you work with, this will have all the different crystallinities as one would expect in the polymer. But the nanowires, which is what you see here in red, it seemed to crystallize predominantly in this beta phase, which, if you remember, I told you is the piezoelectric phase. So there's something about this processing technique that allowed us to isolate this one phase, which is the phase that we were after. So this took us by surprise. We were not expecting this. We were just hoping to form something with better crystallinity, but we found that actually we also have the right phase. And the nice thing is, because these wires are already in a template, it's quite easy to make a device. So, I need to be able to extract the current, so I have to put electrodes onto this device. So here are the nanowires within the template, and I put down 2 electrodes on either side, so it kind of looks like that. And then if you just tap on it, you will see that you get a current response or a voltage response in response to that mechanical input that you're putting in. And quite literally, the first experiments were Richard just tapping on this device, and then we thought, okay, we should actually build a setup to do this in a more in a more repeatable manner, which we did. And straight away we found out that the energy conversion efficiency of the material was about 11%, which, to put in context, if you work with films of the same material, that number is 0.5%, 0.5%. This is already a massive increase in the energy conversion efficiency. And this is simply because we have a more crystalline polymer and we have it in the right phase. And one thing I did mention is this material, what we found is that it's actually self-poured. And what that means is, even with a ceramic, remember I showed you that picture of microstructure with lots of different grains. So even in a ceramic material, you have crystallites with different grains, and each grain might have a dipole moment pointing in any odd direction. Again, if I give you a chunk of barium titanate, it probably won't show you any piezoelectric properties. You have to pole it, which means you have to apply an electric field to get all the dipoles to align in a particular direction. Then it becomes piezoelectric. But what we found is, we were expecting to do the same thing with polymers. Indeed, people do this with films, but our nanowires seem to be self-fold. So we did not have to force anything to do, to align. They just somehow were aligned already. And this is actually something which we looked at in detail in this review that we published a couple of years ago, where typically the way this is done in other polymer systems, so we've got PVDF here, nylon, this is polylactic acid, is typically, you can either draw the material, like physical, mechanical drawing also provides alignment, or you apply like really, really large electric fields, whereas we find that we don't need to do any of that. What we think is happening is that this process of infiltrating the nano-sized pores is equivalent to some kind of a drawing effect, which is what is giving rise to this forming. But we need to understand what these properties are, right? So typically, if you want to understand properties at the nanoscale, because we're working with nanowires here, you would put it, you would look at it under a piezo response force microscope, which is essentially an AFM. It's an AFM arrangement where you have a tip which scans across a sample, and you apply a voltage, an AC voltage, across this sample, so across the thickness. So the idea is, as you apply the sinusoidal voltage, your sample will also deform at that same frequency because it's piezoelectric, and you can measure that deformation using the detection system of the AFM. However, this doesn't work very well for nanowires, and it works even worse for polymers for two reasons. One, it's a soft material, and this is a very sharp tip, so it ends up causing scratches, or it destroys the material. And if you have nanowires, it just moves the material around. So we had to modify this. So I won't go into too many details, but this is some nice work that we've done with a postdoc of mine, Jonathan, who is currently faculty at Technion in Israel, where we developed this novel technique for non-destructive characterization of polymers. And the idea is that we can actually do this in what's known as intermittent contact modes. I won't go into too much detail here in the interest of time, but just to say, we had to actually develop new methodology in order to be able to measure our system of interest. But this was really useful because it allowed us for the first time, it opened up this world of new materials and new length scales using this technique. So with that knowledge, we wanted to kind of see whether we can apply this to other forms, of processing, right? Through which these materials are created. So this was done with this was work done with a good friend of mine, Ula, in Poland, who's an expert in electrospinning. So in electrospinning, what you have is you have a syringe with a needle, and you sort of fill this up with your polymer solution, and you apply a really high voltage, up to 50 kilovolts between this syringe and a collector. And what this does is it results in a polymer jet, and so you can move this collector around, and you can start to form these sort of mats of electrospun fibers. And there's a lot of literature about how you can control the humidity, temperature, etc. to modify the size, etc. of these the microstructure of these wires. But what we discovered is the humidity of the chamber has an effect on the properties, as does the voltage polarity. So whether you apply a positive or a negative voltage, that has an effect on the surface chemistry. So which surface groups are present at the surface. And we wanted to understand whether this had any effect on the piezoelectric properties. So we looked at various PVDF wires, which are done at different humidities, so either 30 or 60%, either positive or negative polarity. So what these images show you are essentially topography of these fibers, and then the piezoelectric response. And maybe this graph is easier to see. You can straight away see that one of these materials has sort of the highest piezoelectric response compared to the others, right? So this is a very good example of where by changing processing conditions, you can essentially change the microstructural features of these fibers, which then changes the functional properties. So that was a nice piece of work, and we wanted to see whether we could do this beyond PVDF. So PVDF is like a very well-known piezoelectric polymer. We wanted to see if we could do this with other materials. So we picked nylon, which is a polyamide, which was known to have piezoelectric properties. People studied it in the 80s, 90s, and then never went back to them. So with Anuja, who was a postdoc of mine, now faculty at back in India, she basically grew these nylon nanowires using the same technique, the same template grown technique. And Yonsik, who was a PhD student with me, he's now faculty in Yonsei University. he really perfected this processing. He really worked hard on getting the right processing conditions to control, again, like I said, both phase and crystallinity. So he controlled things like the temperature during the infiltration process, how to control he found out ways by which we could control the nucleation process, and finally the growth. So the speed at which we would grow these materials had a big impact on the phase that we could get. So here's a nice example where you can precisely control the phase and piezoelectric properties in nylon leather. So here are two phases. So here's the alpha phase, which is again one of the thermodynamically stable phases. This has very strong hydrogen bonding between the various sheets, which actually prevents dipole rotation. So this actually is a non-piezoelectric or non-ferroelectric phase of nylon. Whereas this delta prime phase, which is a metastable phase, so you ordinarily don't even find it in the bulk or in the film, this has, these dipoles are actually free to rotate, which is what you need if you want to make a piezoelectric device out of this. And so again, we went to our PFM, and of course, what we found is that the delta prime phase had a strong piezoelectric response as a function of the applied voltage, but that was not the case for the alpha, which is exactly what we expected. But here's the surprise. There's always a surprise element. We also discovered simultaneously that nylon is a good triboelectric material. So what is triboelectricity? Actually, everyone in the room is familiar with triboelectricity because this effect has been known for more than 2 millennia. It's essentially what we know, we commonly know as static. So if you have two dissimilar objects and you rub them against each other, there's some charge transfer that takes place. And so when you touch something and you get a bit of a shock, right? And you can make these empirical, over the years, people have made these empirical triboelectric series. So there's some materials which are more tribo positive, which means they can give up, they're more likely to donate electrons, and some materials that are tribo negative that are happier to accept electrons. So if you pair like a very tribo positive and a tribo negative material, then you can use this to convert that relative motion between these two materials into usable electricity. So that's the general idea. And because it is a surface charge driven effect, you want to have as much surface as possible, right? To have as much charge transfer as possible. And nanostructured surfaces are fantastic, right? Because there's a lot of surface area that is present. But what we discovered actually is, and we use something called Kelvin force microscopy. So this actually, you can map the surface potential of the sample that you're looking at. What we found was a distinct difference between these delta prime nanowires and these alpha nanowires. Remember, I told you alpha is no good as a piezoelectric, right? But it turns out that if you look at the surface potential, so these are looking at surface potential maps, where we use the tip of the AFM to actually rub the material. So this is before rubbing and this is after rubbing. You can see there's some charge transfer that has taken place between the tip and the nanowire surface. Whereas here there's a lot more charge transfer. Again, same material, like we started with the exact same nylon 11, just difference in processing that is leading to this difference in charge transfer. But what this showed us was actually if you make a device, so this is a typical device, a triboelectric device, where you have your nanowires as the tribopositive material. So that's the thing which I might have forgotten to mention. Nylon is one of the few synthetic polymers that is actually on the tribopositive end of the spectrum. Yeah. So most of them are all negative, but this one is positive, which is great because it means we can pair it with a material like Teflon, which is highly tribonegative. And a simple experiment is just, you can either tap or slide them against each other, and you will produce like a current response in response to that mechanical stimulation. And you can sort of, have a circuit such as this where you can essentially have a load resistance where you can try to work out what is the energy that is being dissipated across that load, and at some point where your input and output impedances are equal, you have load matching and you have a maximum power density. And you'll see that the maximum power density you get from these alpha nanowires is much, much higher than for the delta prime or we used aluminium here just as a control experiment. And the reason for this is, I mentioned the strong hydrogen bonding that you find within these alpha nanowires. And what that does is it actually, because the hydrogen bonding is so prevalent, it actually maintains that surface polarization. Whereas for the delta prime nanowires, because it's free to rotate, it doesn't maintain a very high charge density across the entire lifetime. So this was quite a nice demonstration of a material which may not be a good, well, it's not a good piezoelectric, but it's a really, really good triboelectric material. So with that, with my PhD student Tommaso, we decided to see whether we could actually make a smart triboelectric yarn out of this. And the idea is to electrospin, for instance, in this case, PVDF fibers onto a conducting carbon core. So these are conducting carbon threads, if you will. You can buy these quite easily. And the idea was to electrospin directly onto it these PVDF coatings, so that possibly you could start making textiles out of this. So this will give you what it looks like. So here's your conducting core. Here are the PVDF fibers. This is what it looks like. So it's still quite thick. It's not really it's not quite as thin, but at least it was good for a proof of concept. And what we did was, this is what we wanted to do. We wanted to weave some tribo-negative material with some tribo-positive material to see whether we could make a triboelectric device. So this was our first attempt at weaving. So it doesn't quite look like a fabric yet, but like I said, this is a proof of principle. And we show that, of course, yes, if you rub these together, so for instance, you're wearing clothes, you're moving around constantly, so this rubbing between the fibers can produce, a good amount of power. You can use that to charge up capacitors. So we're trying to show here that we can store that energy in capacitors. So even if you're not using it right then, you can store this up such that when you do need to use it, when you need to power a sensor, for instance, you have the ability to do so. So, just to say, we've done a lot of work on piezoelectric and triboelectric generators, and I just wanted to kind of show a snapshot of both review articles and more recently some roadmaps that we've done, which kind of summarizes this field quite nicely. So with that, I'm going to quickly switch to thermoelectric generators. This is my second example on energy materials. I'll be quick on this one. So again, the motivation is similar, trying to absorb, trying to harvest heat, like waste heat, and convert that into electricity. And the way this is typically done is using thermoelectrics, right? So these are materials where if you apply there's a temperature gradient across it, there's a current that flows, right? It's a transport phenomenon. And so this is, like I said, this is the CVEC effect. Typically, you have doped semiconductors, a p-type and an n-type, in series to form a thermocouple. But these are notoriously inefficient, right? And also some of the best known materials are again inorganic. And even then, around room temperature and for very small temperature gradients, they're very inefficient. So if you have a large temperature gradient, they work well, but not for small temperature gradients. So I was quite interested in looking into organic thermoelectric materials for a number of reasons. One, because you can process these from solution, you can make large areas, they can be flexible for if there are particular applications that need them, and they can be cost effective. They're always cheaper than inorganic materials. So the key figure of merit, or the key parameter of interest here is this quantity here called ZT, and it's given by the CVEC coefficient squared times the electrical conductivity divided by the thermal conductivity. And straight away you can see the problem there. I mean, I want my ZT to be as high as possible. So, I could start by using a very conducting, electrically conducting material. But a material that's a good electrical conductor will also be a good heat conductor, right? So it's really difficult to decouple the sigma and the kappa. But for organic materials, for polymers, the thermal conductivity is inherently quite low, right? So, and there are ways that you can play around with the CVEC coefficient and the electrical conductivity without necessarily affecting the thermal conductivity. And this is kind of what drew us to these materials. And one of the ways that you can build devices, as I was mentioning, is a method called aerosol jet printing, and I'm happy to talk about this with anyone who's interested. But just to give you an idea, anything that you can do by photolithography, we can do by direct printing. So we can get feature sizes down to 10 microns or so, and we can do this over a large area. So you make an ink out of any functional material that you want, and you can essentially start to print or build devices, and you can combine different functionalities as well. And one of the things that this allows you to do is it allows you to actually mix organic and inorganic components. So like I was saying, we want to improve the electrical conductivity without, without messing about with the thermal conductivity. And one way of doing that is mixing organic and inorganic materials together. And we can do this using the aerosol jet printers. It's kind of like having two graffiti cans spraying at each other. The reason this works better than other methods, so typically when people make nanocomposites, what do? They have your organic material, you put in your inorganic bits, sonicate it, try and stir it, and then deposit it. But nanomaterials, if you work with them, you know that they tend to conglomerate, and then they lose the property that you're after. But in doing it in this way, because the mixing is happening sort of in situ while they're, essentially they're in this aerosol form, you have near ideal dispersion of nanomaterials. So you can really hang on to those properties that you want without compromising on the size. And so Camden was a PhD student with me. He did quite a lot of work in mixing, organic semiconductors. So these are the material we use is a material called P.PS. It's quite a well-known organic conductor. And the inorganic part were actually nanoparticles of bismuth telluride and antimony telluride, which again are quite commonly used. And without diving into great detail, what this is showing you is we plotted power factor, which is essentially the S square sigma term here, as a function of the composite loading. Right, so that's how much of the inorganic material we're putting in. And we find that there is a range, or there is a value where you have sort of the maximum power factor. And again, note that this doesn't have much of an effect on the thermal conductivity. All the different graphs here actually, so we threw in some multi-wall carbon nanotubes in there to improve the electrical conductivity. In some of the cases, there are surfactants, to help with any residual agglomeration issues. But the main point is, this is a nice method by which we can really start to get the ideal composition. And we can also use this to do something called compositional grading. So you don't have to have the entire device with the exact same composition. You can actually tune the composition as you go along the device, such that along the device you have different regions which are specifically tuned for different temperatures. Because remember, temperature gradient, it's if you have a temperature gradient at the individual locations, you can have vastly different temperatures. So we can tune the material to have the highest power factor as we go along this, the fringe direction. And just I just wanted to, since I was talking about aerosol jet printing, I wanted to just highlight this work that we did with Jenny Zhang in the Department of Chemistry, where we used this aerosol jet printer to actually make 3D structures. So it's not just 2D materials that you can, or 2D structures that you can play around with. You can actually make these nice 2D structures of, in this particular case, indium tin oxide, which is a conducting, transparent conducting material. So let me just give you a little bit of background. What Jenny does is she works with cyanobacteria. These are these fascinating, naturally occurring bacteria which convert sunlight into electricity. So her idea was, well, if we can coat like a lot of electrode area with this material, then we can use this as a way of harvesting solar power. And indeed, people have been trying to improve this photocurrent by just coating cyanobacteria on flat surfaces. But remember, the more the area that you have, the more photocurrent you produce. So again, what do? Instead of going 2-dimensional, go 3-dimensional. And this has proved challenging because you also need the material to be transparent, because you need light to be able to infiltrate. So we used aerosol jet printing to make these transparent pillars of ITO, onto which Jenny coated cyanobacteria. So it's basically trying to wire up these bacteria. So really cool idea. And not only that, by playing around with the processing conditions, she could introduce these microstructural features within these pillars. So instead of just having like a smooth pillar, they had pores and lots of lots of area that could make contact with the bacteria. And what that led to was the sort of highest reported photocurrent from this sort of system that has been reported within the literature, and it's because of these hierarchical features that we were able to get to this really nice printing technique. Okay, I have given you quite a bit of the background, so I will go quite fast on on some of the materials and devices for sensing applications. So I've already spoken about piezoelectric nanowire arrays, and I just want to quickly show you how we apply these to study cells. And the idea is that cells, they react to their mechanical environment. So this is the field of mechanobiology, where if you start with stem cells, you put them on a soft substrate, you might end up with more fat cells, or if you put them on a stiff substrate, you might end up with more bone cells. So we know that the mechanical environment is important. So the idea was to try and use some of our piezoelectric materials to interface with cells so that we could both sense and stimulate by controlling the whatever input we were putting in. So the material we chose was poly-L-lactic acid because this is biocompatible. People already use this material for wound dressings. They're used as scaffolds. And we knew how to make them, so I've already shown you how we grow these materials using template wetting. Callie, who's a PhD student of mine, she showed how, again, you can play around with the processing conditions to change the crystallinity. So we can go from completely amorphous nanowires to completely crystalline, not completely, sorry, semi-crystalline. You can never completely crystallize these polymers. And my student Mike, what he showed was, depending on the crystallinity, so whether you had amorphous nanowires or crystalline nanowires, the cells behaved very differently. So the cells did not need any X-ray diffraction to work out whether they were amorphous or crystalline, but they actually responded quite differently. And this is, so we did an experiment where we were attaching cells onto various substrates. So if you put them on flat, planar substrates, like the amorphous or the crystalline film, you have almost no attachment. But the minute you introduce nanowires, so here are the amorphous nanotubes, you can see there's an improvement in the attachment, and then when you go to crystalline, there's an even higher improvement in attachment. So how can the cells tell? Like, how do they know the difference? So actually what is happening is that these crystalline nanowires, if you could imagine, crystalline materials tend to be stiffer, and we also did some, we reported in this paper that they have higher piezoelectric response, they have higher surface polarization. So these cells are actually responding to this difference in the, not just the mechanical, but also the electrical environment. So this was a really, we got really excited about this and we wanted to go further. So what we did was, so here are the nanowire arrays, as you can see, and the cells sit on top of them. What we did was we embedded electrodes within them so that we could apply electric fields and also, read off electric fields. Because remember, these cells, when they sort of, when they apply forces to the wires, they will produce a piezoelectric response because these are piezoelectric materials. And this is really cool. So what we did was we took a device. So imagine this is like looking at it from the top. These are all this is the whole nanowire array. And what we're looking at here are the number of nuclei that are growing at different places. So it's like a heat map counting the number of nuclei. To one part of this device, we applied ground. So basically, we didn't apply any electric field. To another part, we applied a DC field. So we basically got all the wires to bend, and then they stayed that way. And this part down here, we applied an AC field, so we were causing the nanowires to vibrate slightly, right? And so the way I describe it, it's like you're tickling the cells, but they really, really like it. So you can see that this is where we have the maximum growth of these cells. So why is this relevant? So we're currently working with researchers at Kiel who are trying to use this method to grow neuronal stem cells, or to promote the growth of neuronal stem cells for spinal cord injury patients. So that's so those are some materials. So that's an example of piezoelectric materials that can be used as both sensors and stimulators. And this next example that I want to show you is how we add functionality to microfluidic channels. So microfluidic devices are essentially, you have very tiny channels which direct fluid flow. And generally they're passive. But what we can do with our printing technique is we can start to add in functional coatings within the channel itself. Right? So we're introducing functionality to the channel so that these become active devices. And and one of the things that we can do is we can introduce electronics directly within the channel. So this is some work that we've been doing with Tom and Diana, who are PhD students. So we print these electrodes and then we put the microfluidic channels on top of them. And currently this is what we're using to detect electrolytes and metabolites in sweat. And I can't really talk very much about this. This is currently, we're waiting for a patent application to be filed. But the idea is that this will help remote health monitoring. So you don't really need to go to a doctor to find out if things aren't quite right. And we would be able to do these tests from the comfort of our homes. So the last bit, if you're still with me, is just two quick examples on biomedical devices. So one is the orthopedic force sensors, which is the basis of the spin-out company, and the other is looking at some examples of soft actuators for medical robotics. Right. So what we've done is we've developed force sensors based on microfluidic devices to enable precision joint replacement surgery. So why is that important? What is joint replacement surgery? So a lot of you would have heard of knee replacements or hip replacements, and the point is that the numbers are going up, and this is partly because the population is aging. Changes in lifestyle means that more people need these surgeries. But it's not just, normally we think about older patients needing hip replacement, but actually the demographic is shifting towards the young. So the surgeon I work with, for instance, he runs something called the Young Adult Hip Clinic, and he sees patients in their 20s, 30s, etc. And so when these people come to get a hip replaced, if they don't position, if the hip isn't positioned quite in the right way, this leaves them with lifelong either pain or issues with the implant such that they need to come back for revision surgery. And revision surgeries are never quite as good as the primary surgery. And the reason for this is when a hip is replaced, so basically what a replacement looks like. You have a femoral head, so this is basically what replaces the top of your thigh bone, and you have an acetabular cup, which is the socket in a hip joint, the ball and socket joint. And it looks something like this. It looks something like this. So there's your acetabular cup. There's a plastic liner that goes between the acetabular cup and the femoral head, which is this bit here, and that's the weak point, right? So if the joint isn't properly positioned, there is uneven wear on this plastic bit, and it basically breaks down, and then you have to come back for revision. And the reason why it's so hard to get this right is actually because surgeons have to just rely on field. So they just, when they go in there, they're like, oh, they move the leg around and they think, okay, that feels about right. And if they don't get it right, then, like I said, you have pain. Sometimes you have people with one leg shorter than the other. There are all kinds of things that can go wrong. And given that there are younger patients that are coming in, there's a need to make sure that this is done right so that the implant can last for a long time. So we have designed these sensors to guide positioning and tensioning based off microfluidic devices. This was done with my postdoc, Chin who's now faculty in Glasgow. And the idea is very simple. So here's our microfluidic channel, and you can grow these, you can make these on flexible substrate. And what we've done is we've printed interdigitated electrodes within the channel. So if you look at it, we've got a reservoir here with some fluid. As you apply force to the fluid, or to this reservoir, it forces the fluid to displace along the channel. Right? So all we're doing really is we're measuring the capacitance within the channel, and the more the fluid moves across this channel, the higher the capacitance change. So that's really the idea behind it. And you can make it quite thin and conformable. And just to say, the reason why this has not been done, you might wonder, well, why do surgeons not use sensors anyway? For three reasons. One, it's a very tight joint, so there's very little space to actually get sensors in. Then you might say, well, surely there are thin film sensors that you can put in there. Sure, but they cannot measure the high forces that go through these joints. So typically, thin film sensors will measure a few newtons, but the forces in these joints are hundreds of newtons. So that doesn't work either. And also, it's an odd-shaped joint, so you do need this to be conformal. And we basically solve all of these problems simultaneously. So microfluidics is not something that you normally associate with force sensing, but this is again a nice example where you can add functionality to a device that you don't normally expect. So how do we actually get this into the implant? So this is work done with my student Liam, who showed that you can actually directly integrate these sensors into the liner. And once you have these sensors in place, you can have a complete readout of the force distribution. So we did a lot of finite element modeling to see that for different angles of the femoral head, what is the force distribution that one will expect, and then we went and did it. So here's just a tabletop demo showing how, as you rotate the femoral head in the cup, you can kind of see here the distribution of force. So this is what a surgeon would see in real time, and that would help them get the right position. So this is the idea behind the spin out. So this is the cup. This is the smart liner, as we call it. This is sensor loaded, which is meant to guide the positioning. I have a little video of this, but I think in the interest of time, I'm going to skip ahead. I can come back to this if there are questions. And just to show that these sensors have other applications. So this is a nice example where we've actually put the sensor on the side of this cup here, as you can see. And we have a robot that is essentially following what this person is doing based off feedback from that force sensor. So it's able to apply the exact same force that the person is applying to the cup, which again, you can think of lots of cool applications. We did this for a science festival demo, so that was quite fun. But it got us thinking that there is a push towards introducing robots into surgery, and robots can't feel. So they can do quite a lot of things, but they can't quite feel forces without without some input, and that's why we're developing these. But at the same time, the robots themselves, when you think of a robot, it's always clunky and unwieldy. So we've been interested in the idea of soft robotics to try and use polymeric materials to create robotic systems. So here's one example where we've been looking at shape memory polymer actuators. So we actually make these resins ourselves and 3D print them into these shape memory polymers, and we can control the motion by applying heat, and we do this using resistive heaters which are actually embedded in these fingers. And the second example and the last example really that I have here are these fully printed tri-layer electrochemical actuators. So here the idea is you have you have an electrochemical material here. We use naphthalene, and they're sandwiched between two electrodes. As you apply an electric field, it causes migration of ions, and that causes the material to bend in response. And with this, because we fully printed this structure, we believe we made the thinnest. So this is about 10 microns thick actuator, and because they're printed, you can pattern these quite easily. So you can have all these different funny motions. And the reason we've been developing this is we work with a surgeon who inserts cochlear implants into the ears of hearing impaired patients, and this is done manually, and it has to be done really carefully and really slowly because otherwise there's a lot of things that can go wrong. So we're trying to see whether we can have these actuators along with sensors such that you can have guided insertion, error-free insertion of cochlear implants. This is just at the early stages, but we're really excited about that. So that brings me to the end. So thank you for bearing with me. I know this was a bit of a whistle-stop tour, and I hope you found things which maybe resonated with things that you're doing yourselves, or maybe that you just found interesting. But yeah, functional materials for functional devices, and I touched upon a lot of functional materials and sort of the core areas that we are mainly focused on. So with that, I will stop. Thank my funders very quickly, and of course acknowledge the people without whom none of this would be possible, and that's really hardworking students and postdocs that I've been privileged to work with over the years. So thank you very much.
Thanks a lot, Sohini, for this overview of what you do. I don't know how you can do so many things, so different fields. So now it is time for questions or comments. If you would like to.
Let me break the ice. Thank you very much. It's been amazing work and a very inspiring presentation.
Thank you.
I've seen so many applications, but my mind was like nervous.
Sorry about that.
It's amazing the number of things that you can do with these technologies and the flexibility that can give you to manufacture any kind of shape or. And my question is about that, about industrialization of these processes, because it's kind of a lab thing now for some of the applications. But for example, I was thinking on the piezoelectric polymers. It's amazing. You can have a polymer that can have these properties, but you only have like wires or nanofibers. Do you think that you can expand that to other shapes with different manufacturing processes and have different applications?
Yeah, I mean that's a great question, and honestly, this is something I've been thinking about for a long time. Like, it's great, it's fantastic to show these things in the lab, but when you think about scalability, how do these processes actually scale up? And that is something that we take quite seriously. So in the case of the fibers, methods such as electrospinning, they are used in sort of industry scale processes. Maybe not necessarily these particular functional polymers, but the technology does exist out there. So there is potential, but of course you need to have very good control on the process. And so that's why what we're trying to do is we're trying to build a knowledge base around which you can then start to, like, if you're thinking of a scalable process, then at least you know what are the key parameters that you need to bear in mind. In terms of the shape, there's nothing particular about a nanofiber shape. It can take any shape, and indeed there might be other techniques like nano imprinting or other already established techniques that would give rise to similar features. But again, it's trying to understand what is the role of, for instance, crystallinity. So whatever your method is, you have to make sure that your material has a certain crystallinity or what is the phase that you are after. So I do believe that there is potential. Like template wetting, to be honest, when we started with it, we thought that this has to be scalable because we were producing them in the lab at, very rapidly, but of course we were still doing it manually. So doing this at the industrial scale and doing it reproducibly, I think those are the main challenges. Like there is still sample to sample variability, and until you solve those problems, these will have trouble actually making it out into the real world. But you're absolutely right, and this is also kind of why we're trying to move towards printing, because if we are able to create these nanomaterials in the right phase, in the right crystallinity, then to translate it into a device using an additive manufacturing technique is good because one, you don't waste any material. Whatever you deposit is what was it. These techniques are actually used in industry. So aerosol jet printing, which I mentioned, it's already used in industry. So Samsung uses this to put circuits on some of their curved electronics, the bendable electronics. So they have these machines which are they're industry standards. So the controls there are much better than what we have. So I do believe that those can scale up, but they use them only to deposit like conductors. So hopefully with this, there might be scope to actually introduce functional materials into some of these additive manufacturing processes. But it's always there at the back of our mind. How do we scale this up? And I think that's one of the main issues with nanotechnology in general. It works great in the lab, but then when you want to take it up into the real world, that's when you run into issues. Thank you.
Okay, thank you very much for your nice talk. It's quite huge amount. Even it's complicated to ask because you have to try to remember all the things. Just two questions. First, with the electricity material, the electric materials, you have shown some experiment which is several filaments, and then you use some friction. Then two questions. Which is the frequency of this process?
Yeah.
And second, have you measured the increase of temperature in the contact area?
Mm-hmm.
And third, is what about the influence of this temperature in the change of the phases that you have in your filaments?
Okay, so I'll take them one after the other. Thank you very much for the question. So in terms of frequency, we restrict our measure. So whatever I've shown you today has been at the lower end of frequency. So when I say low frequency, I usually mean sub 10 hertz.
10 hertz.
Yes. So most of the data I've shown you are between 2 to 5 hertz, and that's the range we work with because we are trying to harvest low level vibrations. Again, if I'm thinking of making a fiber, we are not going to be, nothing is moving more than 10 hertz, I don't think. Maybe I do sometimes, I don't know. I probably do, yes. Yes. So that's the frequency range. Having said that, currently my PhD student is actually looking at some ultrasound frequencies, but that is to try and use ultrasound from the outside to power an implant on the inside. So there is no theoretical limit on a frequency that this would operate. The question for the temperature is a really good one. We have never measured directly, but I see where you're coming from because you have a lot of friction, so obviously there's heat. We do see effects of it because there are systems. What we do is we have a lot of fatigue testing that we run over, and we do see signs of wear, and this could be temperature related, where we can see sometimes fusing of fibers. So it could be that locally you have very high temperatures, but to be honest, we have not measured, so that's actually a good point, and it might be something worth looking into. In terms of how that might affect crystallinity, that I don't think we are yet at that range because typically the materials that we work with, if you want to change the crystallinity, you have to get almost close to the melting temperature, which in our case is like, above 150 degrees, close to 200 degrees, like for nylon. And I don't think even locally we get there, although it's worth. This might be a good thing to model.
The question is because you have talked about metastable phase.
Yes. No, you're
I don't know
right.
if maybe in some part.
Yeah, no, you're absolutely right, and that is possibly something we could look into. Like I said, we see effects possibly of it, but it's not universal, like in localized spots. So yeah, no, it's a good
local increase of temperature.
No, it's not a global. But it's
okay, and the second question is about the sensor in order to measure the forces that you obtain when you introduce the implant.
Yes.
And my question is, this sensor, after to introduce the implant, keeps in the body? And then what about the wear resistance and other?
Yeah. So this is a question I get a lot, and I should have mentioned. So, ideally, we would love to keep it inside the body because my surgeon, for instance, the surgeon I work with, he wants to understand, how forces are distributed in the hip post-surgery because nobody knows. No one has ever measured these, right? And that can have a lot of, there can be a lot of useful information in terms of, post-surgical interventions, etc. So he would like that. But if we leave the sensors in there, it becomes what's called a class 3 medical device, for which the regulatory hurdle is enormous. So the idea is we are not actually, maybe this is a good time I can show you the video. I didn't show you. The idea is not to leave them in there. The idea is to use them only during the trialing process. So let me explain. When the surgeon does this insertion, they don't just put the final implant in, right? They have a box of like 16 implants and they try different ones because everyone has a different size hip. So, so our idea is to put the sensors in those trial implants. It's already part of the surgical process. The surgeon does it anyway. So during the trialing process itself, when they try these different things and they rotate the leg, etc., this is what the surgeon would see, right? So our sensors are embedded within that trial implant. And this will allow the surgeon to find the optimal position, the optimal angle. There's something called the offset, which is what they use to get the right tensioning of the muscles. And this is why sometimes you might have one leg longer than the other. And once they have all of this information and they know what that optimal position is, then they can take it out. And they have rigs in place which can note what this optimal position is. So once they've taken that, then they throw that out and then they put it the right inside. So it doesn't stay inside. But as I was explaining, because I got this question earlier today as well, the other issue of leaving the implants inside is how do you power them? Right? You need to power them. So you could think, okay, I can put a battery, but first of all, again, there's not much space there. But even if I do manage to get a battery in there, what happens when the battery dies? So that's where the other side of my research kind of plays in, which is, can you actually harvest some energy from the body? Maybe not to run the sensors continuously, but maybe to go hand in hand with the battery to extend the lifetime of the battery, perhaps. So for now, it's not a class 3 device. It's going to be so it will be part of the trial liner and not be left in the body. That's the next stage.
Regarding with that, I was thinking that if your surgeon wants to know what happens as you use the implant, what about using leaving the using this as a model? Like you have the.
Oh yeah. No, that's it's
because,
funny. Yeah. So right now, at this moment, we are building a rig to do exactly this. Because like I said,
you have that data.
Yes. So we contacted a company in the US who make realistic leg models, the right weight and everything. And so the idea is to try and hook that up with this to be honest, that's not what we were planning to do. We just wanted to mimic the surgery. So we just to say we have tested these in cadavers. So we've done those tests, and at the moment we are waiting for first in human trials, which will be probably next year or so. But we have to get through all the regulatory bits first. So the idea was, in the meantime, if we can use this leg to go through the motion, I think that's a good idea. We can actually just try and see what happens. Yeah. Get a model. Absolutely. Yeah.
Regarding the mechanobiological application, I have one question. When you put the cells in the pillar, you stimulate that with a fixed frequency, or you have changed the frequency and see different effects?
Yeah.
Or?
Again, this is a great question and one that keeps me up quite a lot. So at the moment, we have used 1 kilohertz, but not for any reason in particular. There's some work by a group in Glasgow where they have stimulated bone cells into growing using 1 kilohertz. So we thought, okay, we'll start from there. But there's no particular reason why we picked that frequency. The question about varying the frequency, this is really what we want to do, and these are currently experiments that are ongoing. So it's not just the frequency, but also the amplitude that we apply, so the amount of and also the amount of time that we. So these experiments are all done over 72 hours. We leave them just vibrating over 72 hours, and then we look at what happens at the end. So whether time has something to do with it.
So you have a breathing 72 hours continuously.
Yes.
Maybe you can do gaps.
Chop it, yeah. So absolutely, but we're not yet sure like what is the ideal time frequency amplitude. But these are currently measurements that we're trying to do. What we found is that very low frequencies don't give us. Maybe we have to wait longer. Maybe 72 hours is not enough. I don't have a feel for it, but this is a great question, and we've asked these people in Glasgow, why did you pick 1 kilohertz? And honestly, the answer was because by accident almost, like it worked, and then they were like, okay, we don't change this. Then it worked. Yeah, but I don't know of any physiological, process that, specifically uses a kilohertz. So this is a good question, but we went with it just because it was reported in the literature. So this was not.
Okay, guide.
Yeah.
Because of the guide. When we work, one of you.
Yeah, that's 1 hertz. I'm saying 1 kilohertz.
Kilohertz.
Yeah. Much higher.
Anyone else?
Yes, I finished, so my question is more about for example, when you made the nylon wires, you said that there were 2 phases.
Yes.
But you only try with one kind of nylon and one molecular weight, or there is differences observed, or?
Yes, so we have only worked with one kind of nylon, so maybe I should have mentioned that. So we work with nylon 11. And the reason is because you only see piezoelectric effects in odd numbered nylons. And the reason for that has to do with the dipoles that are present. So the dipole, if you have an even number of carbon atoms between the two amide groups, then essentially you have opposite dipoles, so it cancels out. So it only works it works better for odd numbered nylon, because then you don't have cancellation of the groups. The reason we picked nylon 11 is because the material was available. But again, people have done this for nylon 7, I think nylon 5, there is work. People do work with nylon 6 as well, and it's, there is a difference in the piezoelectric response. So that's why we work with it. So was the question,
I got, I haven't understood the odd number thing, but it was more, my question was more oriented to molecular weight. I mean, long exchange, short exchange, is there any effect? Or?
Again, we have stuck to one molecular weight because the more things you change, the more things. So these are, I think, 50,000 or so. That's roughly what we use for all our polymers. But in terms of, I believe there will be an effect in terms of how easily they crystallize it and what phase they crystallize in. But for the sake of not changing too many things, we just stick to the one throughout all our studies.
Okay.
Anyone else have a question? Sorry, then I think
then it's my turn to close this session on behalf of the SAMCA chair and the Aragon Institute for Technology for Engineering Research. First of all, I want to apologize for Alfonso Ortega, who is the director of the chair and couldn't be here today. Second, I want, of course, to thank you for this amazing talk, and of course, Julia, for chairing and introducing you and chairing this session. And well, this embodies in a little gift that should be here. So this is for you, and it's a souvenir for this talk.
Thank you so much.
Thank you, and I want to ask a big applause for you.
Oh, thank you.
Thank the Engineering and Architecture School for making this possible, together with the Institute, the Research Institute, and the SAMCA chair. And finally, of course, on the attendance here at home in the streaming, and those who will watch this video afterwards. And finally, I want to invite you for the next session that will be in 2 weeks, and we will have
a former student of the school, a former colleague of the institute, who is now Isabel Garcia, who is now a member of the European Parliament. We talk about her work there. And so with this, we close this session. Thank you very much.
Thank you very much.